Okay, I think we'll go ahead and get started. Welcome back, everyone, to our distinguished seminar series. It's a pleasure to have you all here and welcome our guests who are tuning in. As always, I'd like to thank Howard Weeder and the Canada Excellence Research Chair for underwriting this seminar series. Remind you, next week we have Kevin Bishop from Swedish Agricultural University, who will be talking about boreal forest biogeochemistry. So we look forward to that talk. And also tomorrow there's a talk by Steve Chapra from Tufts University. It's in the agricultural building at 9 a.m. You can check the Global Institute newsletter for coordinates if you're interested. But that should also be a very interesting talk for those in water resources. But today it's a great pleasure to welcome Hubert Savenije from the Department of Civil Engineering at the Technical University in Delft in the Netherlands. Hubert is a professor there. He's head of the Water Resources section and has a really rich history, I think, in water resources. After his undergraduate master's degree, he spent 6 years in Mozambique working on very practical water resources problems, and students today in the class heard some of that experience and how that's affected the approach Hubert takes to some of his research. He was then a faculty member at the UNESCO IHE in Delft. This is UNESCO's water university, if you like, from 94 to 99, and then from 1999 until now, he's been at the TU in the water resources section. Hubert is an international thought leader in water resources modeling, estuary processes, and many other topics. You'll hear of some of the wide-ranging interests he has. He is the current president of the International Association of Hydrological Sciences. He's outgoing editor-in-chief of HES. This is the Hydrology and Earth System Science Journal of EGU, the top-rated journal in the water field. And he's past president of the European Geophysical Union. But he's really been acknowledged for much of his contributions. I think he's our only knighted person coming to the seminar series this year. He's a Knight of the Order of the Netherlands Lion. So we'll hear more about that perhaps over beer tonight. He's winner of the Darcy Medal from the European Geophysical Union, the Master Award from the Technical University in Delft for most distinguished teaching, and you'll get a sense of his engaging teaching style here momentarily. And now this year he's been made a Fellow of the AGU, something restricted to just seven researchers this year in 2014, so quite an accomplishment. And it's just a thrill to have Hubert here and to deliver this lecture. And he's going to give you some perspectives, I think in two parts, about landscape controls on and links to watershed modeling. So, Hubert.
Thank you very much, Jeff. It's really a great pleasure to be here. I already had a taste of what's going on here, and it's really impressive. I'm very, very happy to be here in this remote part of the world, but the center of gravity of water research. So thank you for inviting me, and I hope that I can also present something that deserves the name of breakthroughs. To be invited for a breakthrough seminar is already great. I indeed plan to talk about two things. I first will talk about landscapes, and then I will talk about the moisture storage capacity in the root zone, which is a key element of hydrological models. But first, something on landscapes. I have to acknowledge here my co-workers on this. It's not something that I've just dreamed up myself. It comes from several years of working together with people and also with Jeff, because Jeff was once a visitor of mine. And the first, the start of this is a paper in HES that I wrote a couple of years ago, where I say that modeling in hydrology is really an art. It's not just science, it's also not technology, it's a lot of imagination and creativity in coming up with new model concepts. So you observe things in the field and you try to translate it into a model. But then what is a model other than your hypothesis of how nature functions? And too many people think that a model is something you take from the shelf and apply. And I'm sure you don't share that view, so maybe I'm preaching for the converted. but it is extremely important that you realize that a model is just your perception of reality. And that perception is, of course, a dynamic thing that's changing with your experience and with what you observe in the field and the interaction with other researchers. And after that, I wrote this more opinion paper in what can topography tell us. It's obvious that the topography is the result of water moving through the landscape. The topography is the result of water shaping the earth in collaboration with the ecosystem. They have shaped the environment. So what we see in the landscape is in fact a manifestation of hydrology at work. So how can we translate what we see in the landscape to our models? And the topography is the easiest part of it because that is just the shape of the landscape. So what can we do with it? And in this paper, I explain how I use topography to classify landscapes. So can we read the landscape and translate that into model structures? That's the big question. Or, as Kees Bevan called it, can we map the landscape into the model space? It's a more, maybe a nicer way of saying it. And we have to realize that landscapes have shape and that they have structure, not only what we see on the ground, but also under the ground. There is structure there, and that there is a land cover that has co-created that structure, that lives on that structure. Now, I've always been surprised that so many landscapes that look different or that have a different geology still can be mapped hydrologically in the same way. I give you 3 Luxembourg catchments that some of you know. The Weierbach we discussed today. The Weierbach is a schist geology, which has Jeff's spill and fill characteristics. And the top one is a clearly layered catchment of sandstone. And the lower one is also layered, but with marls. And although the geologies are different, these two can be mapped in almost the same way in a conceptual model, whereas the top one is different. And it has, of course, to do with groundwater being dominant in the top one, whereas groundwater is not dominant in the lower ones. My former PhD student, Fabrizio Fenicia, wrote a very nice paper on that in hydrological processes, where he developed this flexible model structures approach with which you can describe these different landscapes. I really recommend this for further reading. Now, Jeff also once said, and I don't know if you still say it, that it's surprising that so many landscapes in different climates and different geologies still map in a similar fashion. They sort of have the similar behavior. They may not have the same parameters, but they use more or less the same physics. And this is surprising. Or it's maybe not surprising because our physical laws work the same in different parts of the world, fortunately. Yeah. Now, I'm going to give you an example of some work that was done by one of my students, Hessel Winsemius, before I recognized or could translate these landscapes into the model space. So here we did not use the landscape, but we used conceptual models based on our perception of how, in this part of Africa, the hydrological system worked. And it was mostly Kalahari sands that drain towards dambos, which are wetlands, and where you have a structure that during the wet season, these dambos fill and connect, so it's a surface drainage system, and during the dry season, there are lakes that are not connected, maybe even similar to what we see here in the prairies. And the conceptual model that we then made consisted of 2 speeds, you could say. And this is the part of the catchment that is connected to the drainage network, and this is a part of the catchment that is very remote, that we today discussed is maybe recharge dominated. It's rather far from the runoff system. And this is our well-known Xinjiang variable threshold soil model. And with that, we had no data, so it was a really ungauged basin. We could mimic the stocks, the storage fluctuations that we had observed by grace, by gravity. And this was only when we had 3.5 years of grace data. Now we have more than 10 years, so we could do this a lot better. But the essence of this model was, it was one model structure, but distributed accounting of these stocks. And we could forecast rather nicely hydrographs, which we could only validate in 1 year with a water level recorder that we had placed in that stream. But here you see the distributed accounting of precipitation, of soil moisture, and of evaporation. So it was one model structure, but distributed accounting. Now, there is a flaw here, and that there are different landscapes and different ecosystems, and we didn't take that into account. And that worried me. So I wanted to do more. Landscape matters. What can we do? And for me, a landscape is, in hydrological terms, defined by the dominant runoff mechanism. We all know that in riparian zones, or areas where the groundwater is close to the surface, the dominant mechanism is saturation excess overland flow. And we know that in hill slopes, we have Jeff's mechanism, which you could call storage excess subsurface flow. So let's try to identify these landscapes on the basis of topography. Now, there we come to this paper on topography-driven conceptual modeling. And the idea came when I was driving through the French landscape. It's typical French or Middle European stuff. You have the lowlands, which I call for the ease wetland, but wetland means the dominant mechanism is saturation excess overland flow. Then you have the hill slopes, which are generally forested because you can't do agriculture, so in Europe they do forest. And then we have the plateaus higher up, and generally in Europe they do agriculture there because that is easy, it's rather flat and very fit for agriculture. And then you have 3 conceptual models. This is the conceptual model for saturation excess overland flow, conceptual model for rapid subsurface flow, and this is essentially a recharging conceptual model. And then what we do, we try to identify in the landscape where these areas are. And what do we use? We use what we call the elevation above the stream, which is in fact the hydraulic head. And you can show that if the hydraulic head is low, you are in a wetland. If the slope is steep, you have a slope, a hill slope. But here, your slope is small, but you're high above the stream. So with these 2 indicators, hand we call height above the nearest drainage, developed by a Brazilian team of Renault and Nobre, with slope and hand we could classify these catchments. And then attribute conceptual models to it. I'll give you an example of how that is done. It's work of Shervan Harari, who some of you may know. This is the elevation map. This is the hand map. This is the slope map. And this is the combination of the two. Now you can easily see that high elevation still can have a low hand. So you can have wetlands on, you could say, the water divide. And if you have been to mountainous areas, even in saddles of a mountain, in passes, you can have lakes. So high up a mountain, you can have lakes. And that means that this will behave like a wetland. So wetlands are not only down under, they are also sometimes up. So these are areas where saturation excess overland flow can occur. These are the hill slopes, and when you combine them, we have these 4 landscape elements. Wetlands that can be sloped. If they're sloped, they're more like riparian zones. These are plateaus, and then here you see these blue parts, which are wetlands. And then we used the percentages of these landscapes with the conceptual models. And that worked very nicely. Here you see that model with the 3 landscapes which are connected through the groundwater, whereby this is recharged and this receives water by capillary rise, and they are connected through the stream network. But they don't spill one into the other. They are in parallel. And that makes it so powerful. And here you see two performances of the model during a wet season and a dry season, and the scales are different. There's a factor 5 between them. So these are much lower values than this. But you can see that here it is dominated by these blue peaks, which are the wetlands, and this is dominated by the red peaks, which is the hill slope. In Luxembourg, and also today we discussed this, you need higher saturation levels in the hill slope before they connect. And you see that in the wet season, these hill slopes are often connected, and in the dry season they're not. But the wetlands still function as wetlands. So you see that in the dry season you get dominance of wetlands, and in the wet season you get dominance of hill slopes. And then we got very nice duration curves for the topography-driven model. So more realism, but we have more parameters. Now, everybody will tell you that if you have more parameters, it's easier to fit a model. So now the question is, you have more parameters, but what about the predictive capacity? Is that also better? Now, my student Shervan Gerari did something very smart. He then first, and this paper is in HES, it's open access. I'm making a little advertisement for HES, so you can all access this. Some of you already did. He did 3 things. He first ran the model with, let's say, ranges of parameters from the literature in an uncalibrated fashion, but constrained. And I will tell you what we mean with constrained. Constrained means that it is logical to assume that the hill slope has a higher interception capacity than the wetland. And that the hill slope, which is forested, has a higher interception capacity than the plateau, which has agriculture. Also, the hill slope, which has forest, has a higher root zone storage capacity than the plateau and the wetland. So you impose conditions, which we call here constraints. That means that certain parameter combinations are not considered realistic. You throw them out. You don't consider them. And then you don't calibrate the model, you just run it. Now clearly a lumped model cannot have conditions. So here you see that there's a huge range of model outputs. But in the constrained one, you see that there is a band of feasible models. And you see that it has a Nash-Sutcliffe coefficient of 71%. Uncalibrated, purely conditioned. And that this, of course, has a very low Nash-Sutcliffe. By the way, here we considered only wetland and the rest, and here we considered wetland, hill slope, and plateau. So we did gradually more structure in it. This is calibrated and constrained. And now you see that the lumped model performs the best, 91%. That means that these kind of models, which look like HBV, they are perfect curve fitters. You can fit them very nicely. And this one is, of course, lower because you have thrown away a lot of feasible, or you have thrown away unfeasible model parameters, but there are less degrees of freedom. And then we took these models and calibrated them. Invalidated them. And when you validate, so you take these calibrated and constrained models and you run them into validation. Now remember the 88 here and the 91 there. The 91 drops to 75, whereas the 88 drops to 80. That means that from 88 to 80 is a small drop, but from 91 to 75 is a big drop. That means that you were overfitting the lumped model, and you were not so much overfitting this one. It means that this is a more realistic model than the top one. Okay, but now this was a simple temperate zone catchment in Europe. Now we are going to test this in China in a landscape which is semi-arid and cold. It maybe looks a bit like where we are here. And we went to the Gege in China. This is also published recently in HES, so you can access this as well. The Gege, I must be a bit faster, because my time will soon be up. I can't even see my watch. Okay. It is mountainous and cold. Here you see the land cover that exists. There are only a few stations. There are only 1, 2, 3, 4 rain gauges. But there are fortunately 2 subcatchments with stations. So here's an outfall with discharge, and here are also 2 discharge data. Now this is what it looks like. You have really mountains with snow on it. You have hill slopes. You have grass hill slopes. You have wetlands. And you have rocky, bare soil. And these are these different landscape classes that we got from land use maps. What we then did, we started to classify them according to our landscape classification. Then we got wetlands, terrace, grass hill slope, forest hill slope, and we took above a certain elevation, we considered it as bare rock. So purely topographical, and also looking at the aspect of the mountain, because the aspect told you whether it was forested or grass. So classification purely on topography. And then we compared that, and it looked very much the same, and we decided for easiness sake to combine terrace and wetland. And then we ran the model. But you see here that the total basin and these 2 sub-basins, these nested catchments, have different landscape combinations. So the landscape combinations are different in percentage. This is the conceptual model that you would use in a lumped fashion. And this is the conceptual model that you would use in a landscape distributed way. This is the bare rock. This is the forested hill slope and the grass hill slope. The difference is purely the root zone storage capacity. The rest is the same. And this is the typical wetland conceptual model. And they're connected by the groundwater. The numbers here reflect the fluxes, but I'm not going into details because that would take too long. The interesting thing is we calibrated and validated on the outfall, but we also validated on the nested catchments. And then you get very interesting result. In calibration, they don't differ much from each other. This is lumped. This is lumped with distributed forcing. This is flex, but not constrained. And this is the FLEX-topo constraint with conditions. And you see they don't differ much, although the topography-driven is the best. But in the validation, you see that the topography-driven performs much better. The black is observed, and you see that the blue in the validation is almost completely on the observed. More important, however, is that in the 2 subcatchments, the only one that performs reasonably good or close to the observed is the topography-driven, because the composition of the landscapes is taken into account. And if you look at the specific hydrographs, you also see that the lower one gives by far the best performance. But more interesting is an odd event, a very odd event at the end of the wet season. There was the highest intensity rainfall, particularly in this subcatchment, and also in the average, but particularly here. The lumped model gives you a big peak here, which you see in gray, but the topography-driven model is not getting the peak, because you have considered the distribution of both the landscape and the drivers. So the realism of this topography-driven model is far more than the lumped model. And here you see where the water comes from. So the lower one is the groundwater, this is the wetland, and the grass is yellow, the grass hill slope. The forest hill slope generates almost no runoff, and the red is the bare rock. So you can also track the source of the water. Very interesting stuff. Just to show off the result, you can see that the only model that in nested catchment validation performs the best is the topography-driven model. So landscape is crucial both in upscaling and downscaling, but also in transfer of one catchment to another. The landscape holds important information. And we're trying this also in other places in the world. I'm not going to present that now, although one of my students did very nice work in Malaysia, but I don't have time for that. But I would like to now move, before you start applauding, of course, I would like to move to the other presentation. Because this was still done on the basis of calibration. And the most important parameter to calibrate is the root zone storage capacity. And if you have a beta function or the Shenjiang model, then these two are also interconnected. So you always have equifinality between the root zone storage capacity and the beta function. So is there not a way to determine this root zone storage capacity in a different way? And I'm an engineer, and many of you are maybe an engineer, and I know how we as people organize our storage. We do that by the ripple diagram. Let me just go back in time. The start of the Anthropocene, the first thing that we did was just tapping the resource from the river or from a hole in the ground. And soon we found out that if you want to have secure supply, you have to regulate the variability in the flow. So what we started to do is building reservoirs. And we started doing that about 5,000 years ago, here in Yemen. This is at least the only proof we know of 5,000 years ago. But how do engineers do that? They accumulate the inflow and the demand. The inflow is typical seasonal, and the outflow, let's say, is a constant, but it can also vary, of course. And then the only thing you do, you make tangents to the top and the bottom, and the difference between those is the storage you would have required to provide your demand without shortage. And then, if you want to design your reservoir, you analyze all these peaks, you rank them in a Gumbel line, and you, for instance, decide, I take the storage capacity of once in 10 or 20 or 50 years, or whatever. Now, are we the only ones so smart, or are ecosystems also doing that? Do the ecosystems also know the ripple diagram? Well, a little intermezzo. I'll show you, because it's easy to brag about things, let me just show you a weakness of the Dutch. Yeah? So I'm going to show you something that I think is terribly wrong with how we are doing hydrology in the Netherlands. On the left, you see the evaporation in a few months in the dry year, June, July, August, September. And there you see how much evaporation it was. It's based on a combination of eddy flux towers and leucimeters and remote sensing. Let's, for the sake of the argument, say that the left is the truth. The right is what follows from the most advanced, so-called physically based model that we have in the Netherlands, using Richard's equation with preferential flow and everything in it for the top layer and a groundwater model below that. And all the information on land cover and soils, whatever you need. Now just look at this month of July. It is, I must say, a beautiful picture, but it is completely different from what actually happened. In fact, what we have here in Holland, you think it's all flat. It's not. We have a mountainous area in the middle, which is a ridge that the ice, in the ice age, put there. It's sand, and there is forest on it. In this month, according to the model, all the forest died because it was blue, so it was not evaporating, so our forest was completely dead. But if you look here, the part that evaporated most is exactly that forest. It's evaporating 4 millimeters per day. So how is it possible that the model says there's nothing evaporating there, whereas in practice, in reality, there was? This is a polder we created with a clay soil. Here it is dark red, and here it is yellow. How come that the model tells you it's evaporating at 5 millimeters per day, which is a lot in the Netherlands, whereas the reality says, no, it was 3. Well, the reason is because they use soil data, and they use a rooting depth that they say maize roots this deep, deciduous forest roots that deep. They multiply the two, and then they get this. But it's wrong, because a forest is not crazy. A forest, when it's on sand, it will root deeper than the book says. Yeah? And if you would have maize on sand, it would also root deeper than when you have maize on clay, of course. Ecosystems don't read our books and tables. So it's wrong. The concept is wrong. You don't multiply soil information with a rooting depth that somebody determined. You think like the ecosystem, and you define the rooting depth that you require to survive. Now, the root zone storage capacity is in fact this maximum value. That's the root zone storage capacity. And if you can determine that, you can predict behavior in ungaged basins. So, how can we determine that root zone storage capacity? Well, of course, not like this. This is the state of the art. Use a soil map, determine the range between field capacity and wilting point, derive rooting depth from the literature, multiply the two, and then this is universally done. I'm not even mentioning all the people that do it, or all the models that do it. Gialdas does it. Most hydrological model that feeds into climate models do it. They all do it. But now let's go back to ripple. Now this is the infiltration. So for the sake of the argument, it's the precipitation minus the interception. There may be some surface runoff, but then the rise of the curve may be wrong. But that's irrelevant, because we are interested in the decline of the curve. You have the average evaporation that you can easily determine. If you have no measurements, you can take it from the Boudico curve. And then the NDVI can help you to scale it between the wet season and the dry season. Now, I use this dry season transpiration, in fact, and I use it as the tangent, and here is my soil moisture requirement, the capacity. We tried this for the first time in some tropical catchments in Thailand, sub-catchments of the Ping, and we determined all these ripple diagrams for different catchments, and then we ranked them on Gumbel lines. So then I can say, well, the ones in 100-year storage that this catchment would need is 600 millimeters. And the ones in 10-year storage is 350. And I did that for all these, or my student, for all these different catchments. And then we compared the calibrated soil moisture capacity with the Gumbel line. And what did we find? That the calibrated one corresponded very well with once in 10 to 20 years droughts. So ecosystems apparently tune their soil moisture storage to a drought of once in 15 years, which, if I were an ecosystem, is close to my reproductive age. So if I tune my roots to once in 15 years, I can survive. If it had been once in 100 years, I would have been surprised, because then they were investing too much energy and carbon and stuff in their roots. If it had been once in 2 years, I'm sure it wouldn't have, the ecosystem wouldn't have been there. So was this a strike of luck? Maybe. It was only one typical environment. So we took the Mopex dataset. And the Mopex dataset has very, very different ecosystem and aridity classes. And we tried it there, and we found that it gave a very good correlation with a once in 20-year storage requirement. And we could, and 10 was not enough, and 40 was too much. And we could correlate it with aridity, with interstorm duration, and with seasonality. Seasonality is very important. The different colors are different ecosystems. But for instance, for grasses that in the dry season go dormant, interstorm duration Like dry spell duration was far more telling. And you can also do a multiple regression, and then you get something like 70%, 80% predictive capacity, or even more. And this was for these different landscape, or for different ecosystem classes. This is Thailand, and these are 6, different American classes. You see that between the calibrated model and the predicted value for once in 20 years, they match almost completely. Now, isn't this beautiful? Another student of mine did it for the globe on the basis of ERA-Interim. And then you see that there is a very big variability. This is the Amazon forest. But look, in this part of the Amazon forest, the ecosystem needs to root something like 350 millimeters storage. But when it's here, it only needs very little. In fact, it needs almost nothing. It probably only roots for stability, because it's raining every day. It doesn't need to root, not for water. It roots because it doesn't want to fall over. So the same ecosystem has very, very different root zone storage capacities. And I've got other work that shows that that's indeed the case, because the climate models cannot get the evaporation right in these red areas, because they combine soil information with rooting depth from a table. So, models are not mechanistic things. Models are alive. The root zone storage capacity, some people call it the storage in the unsaturated zone, but the unsaturated zone is much bigger than the root zone. But what determines the dynamics of a hydrological model is the root zone, because that's the only part where moisture enters and goes, or where the capacity is variable. This is something that's alive. Also, the interception storage is alive and depends on the season. These are not static things. And if the climate changes, this is also going to change. Because if it becomes drier, the vegetation is going to root deeper. So root zone storage is the result of coevolution. If we understand the coevolution, we can predict the root zone storage. And the root zone storage is essentially the result of an ecosystem interacting with the climate. That means to develop my model, I need climate information. I don't need soil information. If I'm blunt, I say soils are unimportant for hydrological modeling. But of course that would be a bit too bold, because there is of course important information in soils. But to do this, you don't need information on soils. In fact, soils are linked to the landscape. If you classify the landscape into the right dominant runoff mechanisms, then soils are implicit. So, thank you very much.
Thank you, Hubert, for a very stimulating talk. We have time for questions. Yes, Saman.
Thank you very much for a stimulating presentation. My question is on the first presentation and the model that you developed. The model looks very interesting, but what I didn't get is that how these three models are interacting, or are they being, are they working independently, and at the end just they add up the amount of runoff by them all, or there is a procedure from one model to route the flow through another?
The answer is yes to your first. That was not correct. I wanted to do Shift F5, which I'm now going to do. Yeah. Yes, they are in parallel. They connect in two ways. They connect through the groundwater, and there is a stream network. So the outflow here adds up into the runoff, but it adds up. So in fact, they run in parallel. And most people find that difficult because they think, well, shouldn't the hill slope feed the wetland? Yeah?
Yes.
Well, maybe so, but when the hill slope feeds the wetland is probably already filled, because the wetland fills earlier than the hill slope. So if the wetland actually floods the wetland, then the wetland is already flooded. So that's not necessary to do. Does the mountain feed the hill slope? No, because the water goes the steepest descent. So once it's in the stream, it will not go up into the hill slope. So they are in parallel. And also groundwater, as we know, goes like this to the stream. It doesn't go like that. It's not that this groundwater first goes through the hill slope before it gets to the... So yes, in parallel. And that makes it so beautiful because you can just treat them as percentages.
So are we assuming that all these models or the part of the watershed that they are representing are connected to the stream flows?
They are connected to the stream, but you can just add it up. Yeah?
Okay.
So you've got a connection to the stream network here, you have got a connection to the stream network here and there, and in the end we are interested in the outfall. What you can possibly do, we've got delay functions here, but these delay functions are meant primarily within the hill slope, and of course what you could do is do a routing. You can have sub-catchments and then route them hydraulically. We haven't done that here, it's often not necessary.
Yeah.
Okay. Thank you. Yes, Sally.
It was a very interesting talk, Hubert. Thank you very much. I have two questions that are partially interconnected. So my first question is about the how much we should basically give attention to that improvement that we have in model performance indices by increasing the structural complexities. What we know as a mathematical modeler, we always want to go for the principle of parsimony, right? So basically we penalize the number of parameters that we are increasing. So basically by just looking at the result you have shown, for instance, the result that we get by a lumped parsimonious model was, let's say, the Nash-Dot glyph of 0.6 in validation, right? And then with the complex, more parameterized model, we get the 0.7. And if we want to just, let's go to a very simple measure, let's say Bayesian information criterion, perhaps that amount of efficiency that has been increased is going to be penalized by the number of basically parameters. So basically, if we don't have this knowledge that you've got about the landscape, right, as a mathematical modeler, we're just going to go and look at the Bayesian information criterion and then falsify the complex model, especially by the fact that we are aware about this lack of equifinality. We know that if we increase the complexity of model,
I'll cut you short.
Yeah.
First of all, it's not only the number of parameters. It is the degrees of freedom that you have. So with more parameters, you could have more degrees of freedom, but not if you match them with realism constraints. And realism constraints are what I was telling you. And so you know that a forest has more storage than a wetland. Yeah? You know that the interception capacity of forest is more than of grassland. So there are things that you know, and these are additional constraints that you impose. And by that, your degrees of freedom rather reduce than that they increase. But I completely agree with you, don't make the models more complex than necessary. The part that we found the most difficult to do was that, that part in the mountains, this part. We were trying to understand how recharge in bare rock is actually happening. Is it happening through cracks in the rock or through the alluvial fan below the rock? And then you can think about that, but it's all realism. And my reply to you, it's great to use Bayesian statistics and all that. You say if you have no information, My point is then go there and go and have a look. If you want to model a catchment without any knowledge, my reply would be, don't do it. So I think it's a non-question. How do you model a catchment of which you don't know anything? You have to go and have a look. And having a look can also be using remote sensing information or using knowledge that people have or pictures that somebody shows you. But you need to try to read the landscape. If you don't do that, then equifinality is everywhere. And then by all means use the most simple model that you can find. But my overall philosophy is also don't make models more complicated than necessary. But here, the model looks more complex, but in fact it's less complex because it has a higher predictive behavior. Mm-hmm. It's closer to reality.
Okay, thanks. Howard next, and then I'm going to look to some of the students in class. Lucy, Eloise, Jacqueline.
I really enjoyed the talk, and I think particularly the second part, which was fascinating. But I'm going to follow on this line because I remember sitting down with Jeff in London maybe 20 years ago and taking a hydrological model and trying to add complexity based on Jeff's field experience. And the end result was that the model was actually less and less identifiable because we were introducing more degrees of freedom. And it's going to take me a lot to be convinced that your complex model there is actually identifiable in any realistic sense. And I wonder if there's something that you're not telling us about the prior constraints on the parameter space. The prior constraints on the parameter space. So, you've got, it's all conceptual, but I assume that you're actually building in a certain amount of information to constrain those properties of the soil stores and so on. Because without that, I just can't see that you haven't got a highly over-parameterized model.
Yeah, this is what we saw here. There are prior constraints. Yeah? The top one has prior constraints. They are in the paper, but if I just say it by heart, the soil moisture storage capacity is between 100 and 500 millimeters. The interception storage capacity is between 0 and 5 millimeters. These kind of things. Mm-hmm. Yeah? So rather wide priors. And because they are so wide priors is why you see this huge band in the lump model. But with the same priors, you get this. And for me, the question is never, is the model good? The only thing that we can say is the model better than what we have, or is this one better than that one? It doesn't mean that this cannot be improved. I'm 100% sure this one can be improved. But it puts you on a track of improvement. And my main point here is landscape matters. And I think when I say landscape matters, you will probably all say, yes, probably landscape matters because it's logical. But can you identify landscape characteristics from a digital elevation map? Yes. This shows that a digital elevation model has information on the basis of which you can do this. You can also go into the field and measure how deep the groundwater is everywhere and see which mechanism is dominant. In fact, I had students doing that and comparing what they observed with what we did. So that we have there's a lot of field work underlying this.
So in some ways, this is like soft data.
Yes.
And you could use kind of a fuzzy membership function to describe the ranges that you'd accept, where you'd reward or punish the model, if you like, for parameters.
We do, by the way, not punish the model or that we favor parsimony. That's not this way. It's just purely constraining on feasible, realistic conditions. That's the only thing. Yeah.
Okay, I'm looking for students in class now. No, in the class, just before we go to Ali. Yes, Lucy.
Here in Canada, we have permafrost and snow in many catchments. Mm-hmm. Can you still follow your methodology and how it could change?
Yeah, why don't you do it? Because there are many things that you can think of. Permafrost, for instance, also rain on snow, rain on frozen ground, permafrost. But I'm quite sure you can conceptualize that in something that looks like this. I'm sure you can. You have to just think of it. And again, somebody said physically based. This is physically based. There's nothing unphysical here. A storage capacity is very, very physical. A time lag is very, very physical. All these things are very physical. They are not Newton's laws, but it's all very physical. And you can introduce, I'm actually working on that with a student of mine, that when this is frozen, I will not allow water to infiltrate. Everything will then just go out. And we make a function of under which condition it's frozen and unfrozen. But I would like to work with people who actually know about this. Because in Europe it happens. In fact, what triggered my interest is that we had one odd event in January where we had rain on frozen ground and all the existing models failed. So it is an odd event, but these odd events are important. And I would like to go to areas where these are not odd events, but regular events, and then improve my model concept.
We can guarantee you frozen ground here.
Yeah.
Yeah.
But the rain on frozen ground, that's what we want.
Thanks for the nice talk. There's a new type of flow processes called Dunton flow. I'm not sure if I'm what it's a. I'm not sure.
What did you say?
Pardon?
What did you say? Dunton flow?
Yes, I'm not sure if I'm pronouncing it exactly. It's a combination of Dun flow and Horton flow.
Ah, okay.
Then guys in Stanford is working on it now.
Dunne and Horton. Okay.
Yeah,
okay,
and it's kind of like I'm asking you this question because you work in different parts of the catchment, wetland, hill slope, and the transition between forest hill slope and wetland that you call it a grass hill slope. And my feeling is that if this process is possible, I'm explaining it now. If it's possible, it should be somewhere around this transition zone between forested hill slope and wetland. The type of this flow is that the water is infiltrating like...
Okay, not too much. I think that in agricultural fields you can have this, because when you have agricultural fields which are plowed, you often see Hortonian flow. But there's probably also lower, say you have an agriculture on a hill slope. I would say that both processes probably occur. And they may even occur simultaneously. Is that what you mean?
No, the process is not like that. It is first dune flow, and after that Horton flow. Dune flow because the water is infiltrating with the rate, which is much more than, the rate of precipitation is much more than infiltration capacity at the surface. But because the hydraulic conductivity, with their assumption, it's just a theory. It hasn't seen so far. I don't know. That's why I'm asking you this question.
Well, again, I would say make a conceptual model that has that characteristic and see if that indeed can explain certain events that otherwise you find difficult to. This is all flexible. You can do anything.
I know you haven't seen such thing in the field in your according to your experiment.
No.
The water
To be honest, I
infiltrates.
haven't seen much Hortonian flow in Europe. I saw it in Africa. There I've seen a lot of it.
No, first of all, it's dune flow. The water is infiltrating because the surface soil is highly conductive, but because of high anisotropy in the depth, maybe exponential changing in hydraulic conductivity, the rate of recharge would be at some point more than the infiltration capacity. And at that time, water, something like a perch water table, the water is mounting until Hortonian overland flow is happening.
Well, I think we can continue this discussion at the bar.
Touch in the bar, definitely. Yeah.
So a couple of announcements just before we end. Steve Chapra is here from Tufts University giving a talk tomorrow morning at 9 a.m. Howard, where is that talk being held? Do you recall? Or does anyone recall? Ag 180? 1E80. Is that right? So Ag 1E80. Encourage all of you to come to that 9 a.m. tomorrow. And there will be a march now to Alexander's to have a beer with Hub. Hub is from Holland. He knows how to drink beer.
Correct.
I think He's throwing down the gauntlet earlier today, wondering if we drink beer in
I
Canada.
was wondering.
So, yeah. So anyway, join me in thanking him for a really stimulating talk. Thanks.
Thank you. Thank you. Thanks, Jeff.
Excellent. Yeah.